Okay, we didn't have anything that you needed to know, right? Biology and perceptron, you already know, so I think that's okay. Okay, okay, just a second. I still need to finish my setup, optimize it for this format. Okay, just like this, good. Good. Okay. When the neural networks appeared in science, everyone talked, okay, we are very close to artificial intelligence, right? And now the robots, the androids will flood the earth and, usurp the human race. But that obviously did not happen because one of the reasons is the application of a perceptron algorithm is very limited. Right, it's a very simple algorithm, and if you want to create something more complex, if you want to create a multi-layer perceptron, right, where you have several layers, and each layer you sum up inputs multiplied by weights, you add them up, and then you have the signal, but that signal can then again be summed up from different neurons. And again, you can have the threshold and again the signal. Well, you cannot train this algorithm in the same way we train the perceptron, the initial perceptron algorithm, right? Because there is just no way to do it. Now, in the same paper that pointed out the limitations of a perceptron algorithm in 1969, authors Marvin Minsky and Seymour Rayford, they identified that to overcome those limitations, well, you sort of need to go from a simple algorithm to a more complex algorithm and replace just a threshold by something that can be differentiable, for example, right? And it took, I think, around like 10 more years or 13 more years, maybe, to come to a solution to that. And the solution, well, first we need something more suitable for training than just a threshold function. And the second is we need to know how to train the whole multi-layer neural network instead of just one layer neural network. And well, let's talk about first the new function. It was, well, it is a very nice function used almost everywhere in machine learning. It's called a logistic function or a sigmoid. And the equation, the formula for that function is this one. So a sigmoid of s is 1 over 1 plus the exponent to the power of minus s. And it looks like this, right? So it's a sigmoid function because it looks like an s, basically. And well, it's a good function to replace a binary classification, right? So before that, we had a function that was either +1 or -1, depending on the sign. And here we have a function that is less than 0.5 when it's negative, right? And it's higher than 0.5 when it's positive. This is a positive space, right? So this is 0. This is positive space, this is negative space. And now we can sort of reform that function to be the probability of a point belonging to a positive class, right? So we can say, okay, now let's see if the probability of x belonging to a positive class is f of x, right? So if y is positive, then this probability is just f of x. And the probability of it belonging to a negative class is 1 minus f of x, right? And it's very useful because we can now, because of sigmoid of minus s is 1 minus sigmoid of s, we can reformulate that in the following way. We can say that the probability of X belonging to a class Y is just a sigma of Y times W transpose X, right? Because if it's positive, then it's a probability of positive class. And if Y is negative, then it's 1 minus the probability of the positive class, correct? Understandable, yes. Nodding your heads, everything is good. Good. Okay. So, and of course, well, this is a better function, but you still need to know how to train it, and you need to define an error function or a loss function. So the error function is how many points do we classify correctly. And now if we have a probability, we can actually apply thresholds and apply all our ROC analysis and precision and recall. Because now we have a function and we can say, okay, we only take a point as positive if the probability is higher than 0.9, for example, right? And not just 0.5. But now we need to define, okay, but what was the correct answer in terms of that function, that logistical function? How do we know if we're closer or further away from the correct answer? If it's just, let's say, negative or positive, that many functions would be the same, right? And that's where we go to a likelihood here. So a likelihood is just the probability of the correct class multiplied, right? So for every point, we take the probability of its class. So yi is the class of xi, and so this is the probability of the correct class, and we want it to be closer to 1, right? So we want our classifier to have, if the point of the class is positive, we want this to be as close to 1 as possible, and if the point of if the class of the point is negative, we want it to be as close to 0 as possible, right? So now the probability of negative class would be as close to 1. And again, we can reformulate that. So we want this function to be as high as possible, right? Well, what is the perfect likelihood if everything is done perfectly? You just can turn on the mic or write in chat. 1, yes, correct. So if everything is perfect, then it's 1. Well, of course, it cannot be exactly 1, right? Because 1 is not reached by a logistic function. So, but it can go as close as 1, as close to 1 as it can. Now, likelihood is a multiplication of many terms, and it's hard to work with multiplication of that many terms. And when we talk about computer and calculation and working with variables inside the computer, right? So the thing we can transition to, and what is actually used in a logistic regression loss function, is called a negative log likelihood loss. Loss sometimes. Well, if you want to maximize this multiplication of probability, then we want to maximize the logarithm of that, right? Still the maximum, or we can minimize the negative logarithm, right? So we can have the negative logarithm of probabilities of the correct class, and this will give us our loss function. So the loss function for logistic regression can be formatted as follows. It's 1 over n, because we want it not be dependent of n. Then we do sum of the logarithms, and this is just a negative logarithm. And if you remember so this is the sigmoid function, right? So if we take 1 over that, we just take that, and this would be the correct answer. So this is a negative log likelihood loss or a logistic regression, right? And we want this to be as low now as possible, right? So if we wanted the likelihood to be as high as possible, the negative log likelihood we want to be as low as possible, right? So it's a good loss function. We want it to be 0 in a perfect world. But how do we actually minimize it? There is no one-step solution. There is no iterative solution in terms of just shifting the decision function by points. Well, we come here to a gradient solution, a gradient step solution. And if you know anything about optimization, mathematical optimization, you probably know about gradient descent, right? But just to reiterate, if we have a function and we want to find, so here, for example, we have a two-component vector W that we want to optimize, right? And we want the loss function to be as low as possible. So we can start from some random point, then calculate a gradient over W, so a gradient of the loss function over W, and then go. So the gradient will point, okay, let me take something. They have everything, okay, black. So the gradient will probably point somewhere here because the gradient points in the direction of function increase. So if we go in another direction, right, so this is minus. If we go in another direction, in the opposite direction, then we'll go in the direction of function decrease, right? And here it's sort of shown the step-by-step decrease, and you find a local minima, or if you're lucky, a global minimum. And again, this picture shows that depending on where you start, you can find different local minimums. So the only thing you need is to have an ability to calculate the gradient, correct? And of course, for a negative log likelihood, it's quite simple, and we can do it. However, if you remember, in our function, we sum up over all points, and we have many points, like 1,000,000 points or 1,000,000,000 points, for example. It will take a long time and probably will not fit in our memory for that process. So the workaround is a stochastic gradient descent, where we calculate a loss function not over all samples, but rather over some subsample. And that subsample or a sample of the data that we calculate a loss function for a gradient descent step is called a batch. So a batch is just a collection of objects, right? So a batch is points from the data set that we calculate the loss on to take a gradient descent step. And well, an intuitively good way to do gradient descent is go over all points in the data set, but batch by batch. And once we go through all points in the data set batch by batch, we will complete what is called an epoch. So an epoch is once we go through all points in the data set. Any questions so far? Okay. Now, again, for logistic regression, it's quite easy. I can do it at home, but the calculation of gradient of this function by W is just, and the logarithm of this function is just, can be easily calculated. This is y times x over that function. So, yeah. Okay, I have a question from chat from Valentin, or Valentin. What is the correct pronunciation? Maybe you can correct me. But that's not a stochastic gradient descent, but mini batch gradient descent, right? that's the same thing, right? So stochastic gradient descent means we do not average over all points in the data set. All right. This is and the stochasticity is introduced because every time we take a random sample, right? So instead of just going into one direction every time, we can stochastically move. And this is actually a good point you're raising there, that this stochasticity actually stabilizes our algorithm because once we go through all batches, we do not always have the same noise in batches, right? So imagine we have some very noisy point, right, in our data set. And if we will calculate gradient on the whole data set every time, then this noisy point will always shift the gradient in the wrong direction. But when we go through batches, like this noisy point will only be in one batch, and every other batch will shift it in the right direction. And this is a gradient descent is when we go through all points. Stochastic gradient is when we go batch by batch. And there is also a very stochastic gradient descent. It's just when we take one point and our batch consists of only one point. Okay, now to a multi-layer perceptron. So we can train a one-layer logistic regression. Right? Logistic regression is just a one-layer neural network. So we can train it by following the gradient descent algorithm. The problem is, how do we translate from a one layer to a multi-layer? And that was invented in 1986, and we now call it backpropagation of the gradient. So we can sort of isolate. So if we just take the last layer, right, this is pretty much just a logistic regression algorithm. Right, so we can calculate every gradient in that neural network, right? Because this is just W's, right? And when we calculate the loss over W, we can calculate the loss over every direction in W, right? Every feature. So this is W1, 2, right? 3, stuff like that. So we can calculate the gradient, but now we need to sort of push the gradient even further. So this is again W, and we need to evaluate the loss function over that W as well. Because once we calculate the derivative of the loss function over every weight, we can shift that weight in the right direction and shift the whole neural network in the right direction. Now, let's introduce some notation because it will help us. So we have layers. So the layers are just numbered 1 through n, where n is the last layer. The first layer is layer 1. This is our input. So these are our features, right? So this is x1, x2, x3. And of course, sometimes there is an x0, sometimes there is not. Right, which is always 1. You can either edit or do not if you think your data is centered. So the W, the lower indices is 4, 2. So this is the number of output neuron. So this is 4. This is the number of input neurons. So where we go, right? So 4, 2 from fourth neuron in the second layer, and this is the number of layer where we go into. So W3, 4, 2 is a weight of the fourth, from the fourth neuron in second layer to the second neuron in third layer. Right. Then the sum of every weight, right? So if we sum up all the weights times so we multiply the output here. So this is X, which is again, well, if this is X2, 4, this is X2, 1, right? So this is the output, this is x to 1. The output, it's multiplied by weight 3, 1, 1, right? So this is, and if we sum all these multiplication, we get the S. S is the incoming signal, henceforth S. So S is the incoming signal into third layer and first neuron in that case. And X is outgoing signal. So S is just the sum, and X is a sigmoid of S, right? So input is going through a non-linear function, in case a sigmoid, or a threshold. It could be a threshold or something else. So this is just a sigmoid of that sum, right? And x1j is just x, which is our features. Okay. Now let's. So what we need to calculate is we need to calculate the gradient or derivative of our loss function over a particular weight, right, somewhere in our neural network. Well, let's use the chain rule, right, and say that the derivative of that function is a multiplication, a product of a derivative over S times the derivative of S over W. Correct? This is just a chain rule. Now, the derivative of SLJ over WLIJ is just XI L minus 1, right? So derivative of that S function over that weight is just an X, because, well, this is just the sum, right? This is just the sum of these coefficients. All right, let's go back. So we want to calculate the derivative of that function by the W, right? Well, it's just X. Because everything else is does not influencing S. So this is just X. And we will denote the derivative of loss function over signal by delta. So this is delta LJ. Like mathematicians are prone to do, just let's denote it something and we'll figure the rest after that. Okay. So now we need to calculate. If we calculate every delta, right, then we have the answer for the gradient over all weights. Now we can, after that, we can perform the gradient descent step. So we need, now we just need to calculate deltas. Okay. So how do we do that? Well, it's called backpropagation for a reason. Let's start from the last neuron, the last layer. So for the last layer, let's say we have this, okay, logistic regression, so only one neuron. So let's say, okay, we have a logistic regression function. So the signal, the incoming signal goes through sigma, right? And the XL is just sigma of SL. And this is our negative log likelihood loss, which we know is differentiable, right? So if this is differentiable and this is just a sigmoid, well, we already demonstrated that we can calculate then the differential of S, right? Quite easy. Now, if we have delta for the last layer, then let's calculate the delta from all the previous layers, right? So let's say we know all deltas up to some layer L, right? So we know all deltas for that layer, and so on. So now we need to calculate a deltas for layer L minus 1. So this is just a reminder what a delta is, and we can disambiguate it to that, again, using chain rule. So via the chain rule, this will just go derivative of L by S L here, right? So this changes. Then calculate derivative of this by this, and then this by this. Right, so just using chain rule. And we need to sum up because, well, we calculate from the previous layer and we connect it to several. So this, for example, connects to several neurons. So all those deltas influence this neuron. Okay, so what are those? Well, this is just delta from the next layer, right? We just change the index and that's it. So this is just delta that we already know we have. This is a W, right? This is a derivative of S over X. It's just a W. We know that too. And this is a derivative of sigmoid function over previous S, right? Because X, again, is just a sigmoid of S in the same layer. Okay, now you know I have a cat. I hope she'll be quiet. If not, you know, she's cute, and I will introduce a welcome distraction into our lectures. Okay, so in that way, we show that we calculate all the deltas for every layer if we go back, right? So we start from the last layer and we calculate the deltas, and then we propagate it back. All right, using this simple formula. So to calculate the delta of this, we just sum up delta times W times derivative of sigma of S. So the backpropagation algorithm goes as follows: initialize the weights randomly. Then we do a forward step where we calculate all the X's and S's in the layers of our neural network. Then we do a backward step when we calculate all the deltas. And then the step, the gradient descent step for every weight is just a gradient descent step, right? Because this is just our derivative of loss function. Correct? Nice. Now there's an asterisk over randomly, and there's a reason for that. Well, you cannot just use any random numbers, right? Because if you use large numbers, you'll create a problem for yourself because you'll be in a weird part of parameter space. What you need is you need to initiate with a small random numbers. And there's like many principles on how to do it, but the rule of thumb is just use a small random numbers. There's a weird law that a good initialization is somewhere between, I think 1 over 6 roots of n, where n is the number of data set, right? One of the rules is you should initiate from that. But, you know, again, there are many rules. So a sigmoid is not just a term for a sigmoid function. You can use many functions, different functions. The most commonly used are right now displayed on the slide. So sigmoid is good because it translates from 0 to 1, which can be interpreted as a probability. Then there's hyperbolic tangent, which is a function. Okay, the picture is not clear, I guess, but it goes from -1 to 1, and it's 0, 0. And it's useful when you need to subtract something in your neural network, right? Especially in recurrent neural networks. We will talk about recurrent neural networks in the lecture after next. But the problem with recurrent networks is their recurrency, right? If you do the same operation over and over, and you just add, you will always increase your function with the increase of the, let's say, sequence that you use. So sometimes you need to subtract, and a good way to subtract is using a hyperbolic tangent function. Now, what actually blew up the deep learning space and deep learning progress is this very nice function, which is called a rectified linear unit, or ReLU. A ReLU is a very simple function. It's 0 when it's 0, and it's x when x, or s in that case. So why do you think that function is so useful? Why do you think it's the most widely used activation function in neural networks right now? Any ideas?
Because neurons can be dead.
Neurons can be dead? And what does, can you elaborate on that thought?
I mean, it depends. Do we know about symmetry in neural networks, like in that course?
Well, again, so I think you're trying to bring something from outside the course.
Okay.
But I think you should just, okay, well, now we walked through the process of backpropagation, right? And the process of calculating gradients. Now, if you look at, so when you compare, for example, a sigmoid function to a ReLU function, like what is the most important difference in those functions in terms of calculating the gradient? Any ideas? Anyone else?
Простая производная.
Yeah, well, it's just faster, right? It's the derivative of the function is very easy to calculate. It's just one, just one over here and 0 over here, right? You don't need to calculate to take the exponent and then to calculate it and then reverse it and stuff like that, right? So this is, in terms of just calculation, it allows for a bigger neural networks, deeper neural networks. And that's why it proved efficient enough in terms of the signal transduction. So it just works, right? Well, it sort of looks like a sigmoid, right? So this is, if I draw them together, so this would be just like a ReLU, right? So this is a sigmoid, this is a ReLU. Well, they're similar enough. But in terms of calculation, they're like a chasm apart. Right, the one is very hard to calculate on your like a chip, and the other one is very easy to calculate. Okay. Yeah, I wonder. So the next thing I need to talk about is different loss function. And well, if you have a binary classification, the best loss function, the best activation function is for the last neuron is sigmoid, and the best loss function is negative negative log likelihood loss, right? So binary classification, you have your negative log likelihood loss, and you have your sigmoid, which is logistic regression function. Now, if you have a regression problem, what shall we use? What is the output for regression? Well, it's a number, right? So let's just have number S. So S would be the output for regression, right? Okay. And what is the loss function? We need something differentiable, right? Okay, what is the common loss function for regression? Yeah, mean square error. Answer from the chat. So a mean square error, right, was just would be, if this is our answer, this would just be s squared minus y squared. Oops, sorry. S minus y squared. So this is MSE. Does it differentiate well over S? Sure. It actually does. Okay. Now for a multi-class classification problem, we have what is written here: a softmax and a cross entropy. So when we approach the multi-class classification problem, we have several neurons as our output, and every neuron outputs the probability of it belonging to a specific class. So the first neuron outputs the probability of X belonging to class 0, 1, or red, green, blue, doesn't matter. So the first thing is we want these probabilities to equal 1, correct? Probability for every class being 1. Now what is, and the second thing is, okay, so here we have S. So let's write S. So for example, S here would be 3, 10, and minus 2, for example, right? So how do we approach the extracting probabilities from these numbers? Well, we cannot use a sigmoid, right? Because we cannot guarantee that the sum of the sigmoids of several numbers would be equal to 1. Then again, we cannot just sum it up and divide it, right? Because the thing is, so that weight 10 is actually saying that the probability of it being second class is a lot higher than both the first and the third class. So what we use is called a softmax. So a softmax is formatted like this. So we take an exponent to the power of S, where S is the signal, and divide by the sum of those terms. So what it will do, well, I think if you're good with quick calculation, well, this will transition to basically something like 0 something 1 here, 0.99, and again point something. So some low number, and this would be the probability of the second class. Once it will go, like if it's close, right? So if you have 10, 10, and 0, right? So this would be 0.49, 0.49, and this would be 0.0. So there is always probability of it being the class, but it can be very, very low. Now, how do we evaluate if we are correct? Well, we sort of follow the same logic as with log likelihood, right? And the logic with log likelihood is let's calculate the likelihood, right? So let's take the probability and multiply it by the correct class. So let's say again, we have this is 3, 10, minus 2. This translates after softmax to point something 99 something, and then we have the correct class. And but now we need to encode the correct class in a vector form, right? So before that, we only have in binary classifications as a +1, -1, right? So, but we now need to encode it in a vector form so we can perform the calculations. So if we want to encode it in a vector form, well, we just sort of have to put it with one hot encoding, right? And it easily interpretable, right? So this is a vector for the second class. right? This would be vector for the first class, and this would be vector for a third class. Correct? Good. So, okay, well, now just let's multiply, right? But we need a log likelihood, so sure, let's multiply this, the correct output, by a logarithm of the probability. So we want this to be maximized. That means we want the negative of it to be minimized, right? And again, so for every neuron, we either have 0, right? Or this, if it's here, it's 0. Or for the correct class, we have a likelihood of that class for that neuron, right? So now when we calculate the differentials, now when we calculate the gradient, we only use that. So we want the probability of the correct neuron to be as high as possible. And if it's not, we then propagate negative flows, right? And if it is, we just say, okay, everything is fine. We don't need to create a high gradient. And from these, we just have nothing, right? These do not introduce the signal because if they are low, it's okay. We do not care about how low they are if they're sufficiently low. Any questions about the softmax? Okay. Now, regularization. Of course, we encounter the problem of overfitting, and it's actually a very, very common problem with neural networks, especially if you deal with deep neural networks. So, for example, when we will talk about our next lecture, we will talk about convolutional neural networks, and they go up into 100 layers, for example, right? So we have ResNet, ResNet 100. There's 100-layer neural network, right? And I think there is even a ResNet 150. So it's a very, very deep, very, very big neural network. And the problem of overfitting is very, very present in that case, because if you have a large, deep neural network, then and you have a small data set, then, well, you just will memorize the data set, right? So let's imagine, for example, we want to classify cats from dogs. So, okay, this is cat, probably dog. How do you do a dog? Okay, with teeth, right? Okay. Yeah, this is a demon dog. Okay, so you want to classify cats from demon dogs. And what can your neural network do? Okay, so it can just take as input a single pixel and say, okay, something that's unrelated even, right? So let's say we have a cat in a house and there's a clock right here, and one pixel here is white. So the neural network can just take that pixel, multiply it through the neural network, say, okay, this is a very important signal, because if there's this one point in the picture and it's white, that means it's definitely a cat, right? And if you have enough neurons, you can do that for every picture, right? You can say, okay, here, if there's like a, I don't know, red traffic light, right? This is red. And if we go again, we take the one pixel propagated through a neural network with big weights and say, okay, if there's a red pixel there, it's definitely a dog, right? So how do we fight it? Well, the first approach is L2 regularization. It's familiar to us. Well, if we have a problem with big weights in our neural network, right? Because this is only possible if these weights, these single weights are high enough. So if we have a problem with those big weights, well, let's just not have big weights, right? Let's introduce another term for the sum of all weights. And let's now minimize both the loss function and that L2 term, right? And this is the size of the vector, and this is a scaling constant, Now, this term of regularization is also called weight decay. Any ideas why? No ideas. Okay, let's calculate. Okay, so this gradient points into some direction where we have the minimum of the loss function. Where does this gradient point? So let's say that's an L2 term, right, of W. So where does the L2 term of W points? This gradient. Any ideas? It's not a hard question. What is the gradient of this vector squared? Well, just that vector, right? Times 2, more or less. So if we take the negative, it will be just, so if we have that vector, for example, right, vector W, then that gradient will just point towards 0. Correct? And if we now add, so our gradient step, right, is W, well, minus, in that case, gradient. Right, so we multiply that by eta and take a step. Right, so we will always subtract something from our vector. Right, so when we take the step, one direction is one step is in the direction of minimum loss function, and another just lowers the weight, decays the weights, right? So first we try to move the weights in the direction of a better function, and then we just lower them. Right, at every step we just lower those weights. Pretty easy. Okay, so this is weight decay, and well, it helps, right? The lambda here is always something low, so we do not prioritize that regularization, right? If we go high enough, we'll prioritize regularization, and we will over regularize, right, in that way. So and that is always a problem. Okay, with neural networks, there are many ways of regularization. Another one is early stopping. So let's say this is a number of epoch or number of batch, doesn't matter. And this is our loss function or error function. Now, if you look at the graph of loss function over epoch on training data and validation data, you will almost always see something that resembles this picture. So you see the training function go to 0, and validation function will start to increase at some point. Right? Well, after this point, we see overfitting. So up until now, we see just a normal training, and now we're overfitting. Right? So we're starting to memorize the data, right? And this leads to memorization of the noise and forgetting of the signal, sort of. Right, so this will lead to increase of the error on validation dataset, because validation dataset simulates new data, right? And if we extracted some dependencies from noise, well, that just will muddle up our interpretation of the validation data. Well, we can do, okay, we can look at that graph and say, let's stop here. Let's say it's 20 epochs, and that's it. We do not train after that. But how will that help us, right? Why do we not just say, okay, this is the best function? We just take that neural network and apply it, right? Why do you need the number of epochs? Well, because if you use your neural network in practice, after you define all the parameters and after you define the number of epochs, the regularization term and stuff like that, you know that these are the best parameters for training your neural network. Well, after that, you sort of want to train on all available data, right? Because what do you need validation for now, right? You already know these are the best parameters. You don't need to find them again, right? So after you find the best parameters, you just merge the validation and training data together and launch with the defined parameters. So you know your regularization term, you know the optimal number of epochs, and you launch with that. Right? So this is why you need the number of epochs and not just take the snapshot of that network and use it, because you want to train on every available data you have. Now, the next type of regularization is called data augmentation, and it's sort of tricky one. So if we say the problem, again, let's go back to cats. If you say a problem is memorizing a specific pixel, let's introduce enough perturbations, enough noise, so that will not be possible, right? Let's increase the size of our data. And what we can do is we can mirror our image, for example, right? We can say this is a cat, but this is also a cat. Now we cannot say, okay, this pixel sort of signals a cat. We can rotate images, but now there's a question if this is a cat as well, right? Is this a cat? Is it not a cat? Well, probably a cat upside down is still a cat, right? Is a car upside down still a car? Or is it some, garbage after that? So you always have to think whether your data augmentation techniques are applicable in your case. So whether or not it's justified to perform some augmentation there. And the most effective thing is just adding noise. So instead of, some transitions, some mirrors, rotations, you can just say, okay, let's add some noise, right? And let's add different noise every time. So in that case, we want the network to just concentrate on like a general shapes and extract some dependencies, extract some laws that it can follow instead of just memorizing pixels, because the pixels will be noisy. Okay. Now, the last thing for our regularization part is dropout. Dropout was introduced with the start of, again, deep learning revolution in 2012. And the idea, again, is quite simple. If we are afraid of a single path being able to memorize some noise and turn it into a signal, well, let's just not use that path in every batch. So let's just turn off neurons from batch to batch. So let's say we have a new batch incoming, then we take and we turn off a portion of neurons. Let's say 0.5 neurons. Half of neurons gone, right? So in that way, again, we want the network to be able to learn general laws about the data rather than memorizing paths. So we turn off these neurons, right? And then the next batch, we will turn off again randomly, we will turn out another half of neurons. And 0.5 is actually a very common coefficient of dropout. A 0.5 is what is mostly used like by default. You can, again, using validation, You can change it and try to find the best one, but 0.5 almost always works. Now, there is a thing to follow here. So when you use dropout, you have to multiply your inputs by a coefficient, right? So let's say I turn off half of neurons. Well, the input now needs to be multiplied by 2. Right? Because I want to sum of the signal to be on the same scale every time. Again, why do we need that? Because when we're done with training and we want to apply our neural networks, we want it to be working, we do not use dropout, right? After we're done with training, we will turn on every neuron, right? Because when we use our network, we want to use it to its full potential. So when we apply the network, we want to every neuron to be turned on, but it will not work if the scale was different on training and application or inference, right? So if the scale on inference and training is different, it will just break stuff. So what we need to do is multiply by the same proportion that we leave the neurons out. So let's say I remove a third of neurons, right? Let's say a third of neurons are removed. What is the coefficient I need to multiply all my neurons by? A third.
Полтора.
Yes, of course. Well, if one third is removed, then there are 2/3 left, right? And we need to be those 2/3. It's the same as 1, right? So we multiply by 1.5. Okay. Great. There's also at some point has been a method called drop connect. Where instead of specific neurons, we removed specific weights. Right. But it was soon, well, it was hard to implement. And that is actually another important point, that when you program a neural network, create some architecture, apply some methods, you always have to remember that in the end, it will have to be calculated on some GPU or a CPU or a cluster. And you always have to think about how much time and how much resources will it take, right? So, and how it's actually, if it can be implemented or not on a chip. So Drop Connect was a very interesting idea, but it sort of fell away after trying to implement it. Same with the ReLU, right? The ReLU is a very simple function, right? And its rise to power occurs because it's easy to implement and easy to calculate. Okay, now, when we talk about deep learning libraries, mostly it's down to two things, TensorFlow or PyTorch. So a TensorFlow is a library that is supported by Google. And it was their in-house library for doing deep learning. They opened it up. And it was very hard to use. It was very directed. It was very adapted to an engineering point of view. So Google engineers used it. And it was very hard to use by data analysts. So that is why some enthusiasts created a Keras library that was on top of TensorFlow. And it helped to just create and new architectures and program neural networks in a very easy way. Well, at some point, Google came to their senses and just included Keras into TensorFlow. So now you can just use Keras inside TensorFlow, and they're just easy to use. At some point, TensorFlow was sort of hard. Most libraries do not optimize towards a GPU usage, and GPU utilization. So a torch library was created. And the first torch actually was Lua torch. Maybe some of you heard of a Lua programming language. Maybe not. It is most famous for creating add-ons for World of Warcraft, but that's pretty much it. It does not have a wide application, but some enthusiasts again used Lua to create a very good deep learning network. But well, a good library is a supported library. So a small company called Facebook started to support and made Torch the in-house library and started to support it. And they actually released a PyTorch library. So PyTorch is Python. TensorFlow is Python, and PyTorch is, of course, Python as well. So when you try to do a deep learning project, you will either use TensorFlow or PyTorch. And the rule of thumb is, well, they're pretty much the same by now, right? TensorFlow shifted from this engineering tool to something that a data scientist can use as well. And the idea is, well, if you're doing a research in a particular area, just learn the libraries that exist in this area and learn whether or not they're in PyTorch or in TensorFlow and just use that. Well, you know, some people do not like Python. So for those people, those Java, you know, brave heroes, there does exist a deep learning for Java library with a small group of enthusiasts that support it. Now, there's also an important thing to say. At some point, if you think about applications, so TensorFlow and PyTorch is something that is used for development. So when you develop your model, you want to train your model, now this is the best tool. But when you talk about application, now you're in a different area, right? You need to know whether or not your neural network will be compiled, will not be launched on some device, for example. But there is a good news there as well. There is something called an ONNX, Open Neural Network Exchange, which is a set of libraries that can take in any neural network in PyTorch, TensorFlow, deep learning for Java, or anything else, and output it as a ONNX file, which is then can be used by different libraries that create executables from these deep neural networks. Okay, so that's it for today. Any questions regarding the lecture? Okay, so hopefully the absence of questions is because everything was understandable and not because you are all sleeping with the computers turned on. Okay, now I see that Oleg is joined us. Now for Valentin. I do not know if you speak any Russian at all, or you just only speak English.
Technically, I do, but I don't think that my vocabulary will be sufficient for that for topics like that.
Okay, so the problem is the practice and the homeworks are in Russian, but let me put you in touch with Oleg directly, who is the head of our practice part. And if you have any question that just you can ask him and he will help you in English. He's sufficient, but just the way we started is in Russian.
Yeah. As long as it's written, it's okay, I guess.
Okay, good. So that is that. And I see Oleg is in here. So I guess we start, I don't know, 10 minutes practice or something else.
Да, мы начнем через 10 минут.
Nice. Okay, thank you for your
Okay.
attention. Hopefully you enjoyed the lecture, and I stop the recording.